All right, welcome to section 4.3. We're going to look at how the derivatives affect the shape of a graph. And actually, I want to argue with this title from the book. I want to use the word describe. Because if you look at the derivative of a function, it can describe the shape of a graph. And here I've got this picture. We see a couple of familiar things. You know, if you see a cusp or a sharp corner here, the derivative is undefined. If we're going uphill here, we see that we have a positive slope. So the slope is positive. That means the function's increasing. If I have negative slopes of tangents, I can see that it is negative or decreasing. Here I have a horizontal tangent. That means that my derivative is equal to 0, and so on and so forth. So we're going to look at all the different ways that the shape of a graph can be described using derivatives. All right, so let's look at this. What does f prime say about f? So this is your first derivative, okay? Your first derivative. So from basic algebra class, a line is rising or increasing from left to right if your slope is greater than 0. And the line falls or decreases from left to right if the slope is less than 0. So we'll now see how the derivative, which is the slope of the tangent, helps us to determine whether a function is increasing or decreasing. So let's look at a test for increasing or decreasing functions. Let's let f be a continuous function on the closed interval of ab, and it's going to be differentiable on the open interval of ab. So if you look at the first derivative, and the first derivative is positive for all x in the interval ab, then f is increasing. So if you have a positive slope for your tangent, okay, you know that your function's increasing. It's going uphill. If your derivative is negative or less than 0 for all x values in the interval ab, then your f is decreasing on ab. Well, it looks like that. Here's the slope of the tangent would be negative. That means it's going downhill. So the first derivative test is a test that we use on the first derivative of a function in locating possible maximum and local minimum points on the graph of the function. Any value c which causes the derivative to equal 0 or does not exist is called a critical number of the function. These critical numbers tell us where locations of local extrema are located. Furthermore, we already saw in this section that the first derivative helps us determine whether the function is increasing or decreasing. And we're now going to investigate how the first derivative might assist us in determining whether a potential extremum is indeed a maximum or a minimum. So let's see what that means. Let's look at our first example. Let's find the intervals on which f of x, which is equal to 3x to the 5th minus 25x cubed plus 60x, is increasing or decreasing. All right, so the first thing I'm going to do is I am going to find f prime of x. I am also going to completely simplify that derivative so I can do the solving. Next, I am going to solve. I'm going to find out where the critical numbers are for when that function, that derivative, is equal to 0. And then next I'm going to look at a sign test for the first derivative. Okay, so let's take the first derivative. Well, that's a nice one to get started off with. It's just a polynomial. So the 5 is going to come down here. I'm going to have 15x to the power 4. And then this is going to come down here, minus 75x squared. And then the power of x is 1, so plus 60. And I don't need to do any more simplifying than that, so I'm done. I'm going to set that equal to 0. And I'm going to solve this function. Now, if I think about my arsenal of pre-calculus skills, in order to solve this, it's not linear, so I can't just like subtract 60 and do stuff. I have to have it, keep it equal to 0. I have to have it equal to 0, and then I need to factor it. So the first thing I'm going to do, take out that 15. So I'm going to have x to the 4 minus 5x squared plus 4. All right, next, and it might not be that apparent to you, but what we have in here is what we call quadratic in form, and we can definitely factor this. For example, would you know how to factor this equation? So if I had u squared minus 5u plus 4. What does that factor into? Well, yeah, right? You're looking for the factors of 4 that add to give you a negative 5. So it's going to be u minus 4, u minus 1. Well, it's going to be the exact same thing, only u, in this case, is x squared. So if you get u squared is going to be your x to the 4, and regular u is going to be x squared. So if I were to factor this, I end up with x squared minus 4 and x squared minus 1, in which I get super excited because both of those are very easy to factor. They're both just difference of squares. So this is going to factor into x minus 2, x plus 2. And this is going to factor into x minus 1, x plus 1. And now I can set all of these factors equal to 0. Well, 15 does not equal 0, so that does not contribute to my solution here. But if I have x minus 2 equal to 0, that means that x equals positive 2. And if I do x plus 2 equals 0, that means that x equals negative 2. And here I'm going to get a positive 1 and a negative 1. All right, and I can verify this with the graph, but now what I want to do is, because this is with my first derivative, I want to look to see what do all of these critical numbers have an effect on my graph. And let's look at that with a sign test. So I'm going to start with my smallest number, and I'm going to write down all my factors. So here I've got a factor of, I'm just going to include the 15 with that first one, x minus 2, my factor of x plus 2, x minus 1, x plus 1. And look at all of those individually. And then I'm going to look at the cumulative effect of that on the actual first derivative. Okay, so my smallest critical number here is negative 2. So I need to pick something on the left side of negative 2, so something smaller than negative 2. So I'm going to pick a test value of negative 3. And then my next critical number is negative 1. So I'm going to pick x equals negative 1.5. That's a test value in between negative 2 and 1. My next critical number is 1. And my critical number after that is 2. So I pick a value between -1 and 1 for this interval here. And this is I'm going to use x equals 0. In between 1 and 2, I'm going to use a positive 1.5. And to the other side of 2, larger than 2, I'm going to pick x equals 3. Expand these lines just a little bit. All right, now what I'm going to do is I'm going to plug values in. I'm going to take -3. I'm going to plug it into each of these and see what my effect is. So for x minus 2 times 15, I'm going to get a negative, because -3 minus 2 gives me -5. -5 times positive 15 is negative. So I get a negative number. For x minus 2, if I plug in a -3, I get a negative number. For x minus 1, I get a negative number. For x plus 1, I get a negative number. Now, if I take a negative times a negative times a negative times a negative, I get positive. And if I plug -3 into my first derivative, I will get positive. So that means that it is increasing on this side of -2. All right, so now let's look at our next region between -2 and -1. We're going to use the test value of 1.5. So for 15 and x minus 2, I'm going to get a negative. For x plus 2, I get a positive. Remember, I'm just plugging them into here. -1.5 plus 2 gives me a positive 0.5. I don't care about the number. I care about the sign. And then for x minus 1, I get negative. And for x plus 1, I get negative. Now, if I look at this cumulative effect, negative times positive is negative, times negative is positive again, times negative is negative. I can also just take -1.5 and plug it into my first derivative, and I'm going to get a negative sign. Okay, and that means it's decreasing. So at x equals -2, I'm going to have a max, because I went from positive to negative. I'm increasing, then decreasing. All right, let's see what happens on the other side of -1. So between -1 and 1, I'm using the test value of 0. So if I have 0 minus 2 times 15, I'm going to get a negative. If I have 0 plus 2, I'm going to get a positive. 0 minus 1, I'm going to get a negative. 0 plus 1, I'm going to get a positive. Also, if I look at the cumulative effect, if I multiply these all together, I get positive. The other thing is I can just look at f prime of x, plug 0 in there, and I can see that this is going to give me a positive number. So this is going to be increasing after -1. So for -1, it was decreasing, then it's increasing. This thing looks like it's going to be a minimum. So now let's take a look at the next region. So between 1 and 2, I've got 1.5. I'm going to plug that in. 1.5 minus 2, I'm going to get a negative. For x plus 2, I'm going to get a positive. 1.5 minus 1 is a positive. 1.5 plus 1 is a positive. If I look at this, a negative times 3 positives is going to give me a negative. And if I just plug 1.5 into the first derivative, I'm also going to get a negative. And so that means that this is decreasing. Notice I've got increasing here, decreasing here. This thing is going to be a maximum. It was a very bumpy ride on this function. Okay, let's look at our very last region for test values. My next critical number is x equals 2. So I'm going to look at values larger than 2. So 3. I'm going to plug those in. So 3 minus 2 is going to give me a positive 1 times 15. Gives me a positive. And then for 3 plus 2, I'm going to get a positive 5. Remember, I don't care about the numbers. I care about the signs of the numbers. I plug in 3. 3 minus 1 gives me a positive 2. 3 plus 1 gives me a positive 4. And positive times positive times positive times positive gives me a positive. I can also just look at the effect of taking 3 and plugging that into our first derivative, and I can see that it's increasing. So and over here I can see a minimum. All right, so noticing what the first derivative tells us about increasing and decreasing, I can say that f of x is increasing on whenever it's going up. So x is the element of, so it's going up from negative infinity to negative 3. And then it's going up again from negative 1 to 1. And then it's going up again from 2 to infinity. And then it's decreasing on those other intervals. So it's decreasing when it's negative. This is going down from negative 2 to negative 1. And notice I'm using open intervals here. The endpoints are not included. And it's going down again from 1 to 2. All right. And this is how I can use my first derivative to tell if I'm increasing or decreasing. Now, this max and min stuff we haven't touched yet, but we're gonna use that decreasing stuff to give us some information. Let's look at the theorem of the first derivative test. Suppose that c is a critical number of a continuous function f on interval I which contains c. If f prime changes from positive slopes to negative slopes at c, then f has a local maximum. So let's look at this. Let's see. Here's a value where I have a maximum. If you notice, slope of the tangent before the maximum is going to be positive, and slopes of the tangent after the maximum are going to be negative. Okay, so it's got to change from positive to negative at the value c. If f prime changes from negative to positive at point c, then f has a local minimum, and we can see that here. Here's a minimum, here's some value c, and before the minimums the tangents are negative, and after the minimums the tangents are positive. If f prime does not change at sign c, change its sign at point c, then f has no local extremum. So there has to be a sign change going on here. So in other words, you've got a maximum if it goes from positive to the negative, from left to right of c. Here's your c value. Okay, likewise, the function has a local minimum at c if it goes from negative to positive. And again, from downhill to uphill. We're just looking at the slopes of the tangents. Okay, but if you have this value, this graph here at c, notice that before the horizontal tangent, the slope of the tangent is positive, and afterwards the slope is positive. This is no extrema because there's no sign change. All right, let's look at this example. For this example here, I'm going to use the first derivative test to find local maximums and minimum values of this function. So when I do this, basically what I'm going to do is I'm going to find f prime of x. I am then going to completely simplify f prime of x, and then I'm going to solve f prime of c equals 0. In other words, find the values of x that make the derivative equal 0, and then I'm going to do the sign test. I'm going to look for changes of signs. All right, so let's take the derivative of f of x. So we need to use product rule because I have x cubed times x minus 4 to the 4th. So I'm going to take the first times the derivative of the second. And the derivative of the inside is 1, so I could write that there, but I don't need it. And then product is plus. And then I'm going to take the second, and I'm going to multiply that by the derivative of the first. Now I'm going to do some simplifying. So for sure I can take an x squared out of everything. I'm going to color code a little bit. So I can take an x squared out of x cubed in here. And then I can take an x minus 4 to the third power out as well. So let's do that. What I'm going to have left on the inside here is I'm going to have 1 power of x, 4 times 1. So I'm going to have 4x here. And my x minus 4 is already taken care of to that third power. I'm going to add to that. I'm going to have 3 times x minus 4. All right, now I need to distribute this out and combine like terms. And I'm going to end up with 3x minus 12, so I'm going to end up with 4x and 3x gives me 7x, and then minus 12. All right, this is completely simplified. Notice I can tell that it's completely simplified because I've got basically factor times another factor times another factor, okay? Another thing would be like if it's a simple fraction. Like if it was written like this, that would be bad. But if it's written in just a simple fraction, that would be good, okay? All right, so I'm going to set this equal to 0. So it's completely simplified. Let's set it equal to 0. So I'm looking for my critical numbers. Okay, so this means that each factor needs to be set equal to 0 and solved. So x squared equals 0, that means that x is equal to 0. If I have x minus 4 to the power of 3 equals 0, that means that x minus 4 is equal to 0, which means that x equals 4 is where the sign is changing. Or might be changing, I don't know. We have to find that out. And then 7x minus 12, set that equal to 0. And I'm just going to add 12 to both sides and then divide by 7. And then don't use a decimal approximation here. All right, so let's go ahead and put them in order. I basically have this function here. And I'm going to kind of mark all the values. Now, if you've done sign tests before, it just kind of depends on how your teacher has shown you how to do it. So first of all, you just want to make sure you have your critical numbers clearly identified. So in the top row, you're going to put your critical numbers. And notice that these little column lines here, these identify exactly where you have a horizontal tangent. All right. Okay. Next, what we're going to do is we're going to plug in values into your f prime of x. Okay, you're going to plug in values into your f prime of x. And then you're going to identify whether it is positive or negative. Okay. You could also, if you look at this, plug in values into your individual factors. You can look at what happens to x and then x squared. And then you can look at what happens to x minus 4 and x minus 4 cubed. And then 7, oops, I'm coming to the bottom here. Need to move up a little bit. So look at your x and then x squared. And then look at your x minus 4 and your x minus 4 to the power of 3. And then your 7x minus 12. Okay. This part, though, gets a little hinky. So honestly, I really am just okay if you look at the actual whole derivative. Okay, so smaller than 0, pick a test point smaller than 0, something like -1. Now next, you got to pick a number between 0 and 12/7. Now 12/7, if you look at that, it's like approximately 1.714. So if I pick a +1 is in between 0 and 12/7. And then between 12/7 and 4 is a number like 3. And then a number larger than 4, I'm just going to pick 5. Now, mind you, I'm just picking rando numbers for this. Okay. Now, I'm going to show all the individual ones first. But remember, you can just do the top row. This will give you some time to kind of appreciate the easiness of the top row. Okay, so if I were to plug -1 into x, I get a negative number. If I were to plug a -1 into x squared, I get a positive number. If I plug a negative x or a -1 into x for x minus 4, I get a negative number. Now I get -1 minus 4. If I plug a negative number into x minus 4 cubed, I get a negative number. And then if I plug a -1 into 7x minus 12, I also get a negative number. Now if I look at this cumulative value, my cumulative ones are here, here, and here, I have a positive times a negative times a negative. So the cumulative sign here will be positive. And I'm at the bottom of the screen, dang nabbit. All right, let me see what I can do to erase that. All right, so this is like your whole. Okay. So a positive times a negative is going to give me positive. So this tells me that it's increasing here. Now, if I were to plug -1 into the derivative, I would also see that this is positive. So it means that it's increasing at x equals 0. All right, now let's plug in 1. So for 1, if I plug in, this is my test value between the critical number 0 and 12/7. If I plug +1 into x, I get a positive number. Plug it into x squared, I get a positive number. Plug it into x minus 4, I get a negative number. Plug it into x minus 4 cubed, I get a negative number. Plug it into 7x minus 12, I also get a negative number. So again, we look at our cumulative effect. Here I've got a positive number times a negative, and this is going to give me positive. So that means it's increasing on the other side of 0. Similarly, if I take x equals 1 and I just plug it into the first derivative, I'm going to see that I get a positive number. So again, it just tells me for the critical number of x equals 0, I'm going increasing and I'm leveling off and then I'm increasing again. So this is not going to give me a max or a min. Okay, so let's look at the next testing region. I'm looking in between the critical number of 12/7 and 4, so I'm going to plug in a positive 3. If I plug a positive 3 into x, I'm going to get a positive number. Plug it into x squared, I'm going to get a positive number. If I have 3 minus 4, I'm going to get a negative number. If I have 3 minus 4 cubed, I'm going to get a negative number. Now I have 7 times 3 minus 12, I'm going to get a positive number. So again, I'm just plugging these values in here. Then I'm going to look at my cumulative effect. So I'm going to have x squared times x minus 4 cubed times 7x minus 12. So it's a positive times negative times positive is going to give me negative. So this one's negative. So the other side of 12/7, I can see that I'm decreasing. And then if I plug 3 into f prime of x, I'll also see that it's negative. So this right here means that I've got a max. Okay, I've got nothing here that I can tell at x equals 0, but I definitely have a maximum at 12/7. So let's look at the next testing region. So I've got x equals 5. I'm going to plug that in. If I plug x into, or 5 into x, I get a positive 5. If I plug it into x squared, I get a positive 25. Do 5 minus 4, that's going to give me a positive number, 1. And 5 minus 4 gives me 1 cubed, and so that gives me 1 cubed is positive. Well, 7 times 5 is 35 minus 12 will also give me a positive number. Then if I multiply them together as they are in the derivative, it's x squared times x minus 4 cubed times 7x minus 12. And positive times positive, positive, the cumulative effect is positive. And if I were to plug 5 into the derivative, the first derivative, I would also see that I get a positive number. So that means that after the critical number of 4, my slopes are increasing again. So if I go from decreasing to increasing, that means this is a minimum. So always verify this with a graph, which if you were to graph this thing, you'll see it's a little tall, but it kind of looks, the regular graph of the function looks like this. And you will definitely see a minimum right here at 4, and a maximum, although it's really, really tall, it's like around 150. You see that that happens at 12/7, and then here you see at x equals 0 that regular f just doesn't do anything funky. It just levels off. So here's going to be our answers. We'll plug it in. So I've got a maximum at 12/7. And if I plug that into the function, oh, I'm going to get a really yucky number. I'm going to write it factored out because it's a little bit easier than all the digits. You can use a decimal approximation if you want to. But specifically, it's at x equals 12/7. If they want the points, you got to give the points. If they only want the x, you only have to give the x. And then you've got a minimum at x is equal to 5. And then if you plug, sorry, not 5, 4. 4 is my critical number. This is 12/7. So I plug in 4. And I plug that into my original function, I get 0. Okay, so I've got a local min at 4, 0, or when x is equal to 4. And these are my answers. All right, so example 3, we're going to use the first derivative test to find local maximum and minimum values of f of x. If f of x is defined as cosine squared of x minus 2 sine of x on the interval 0 to 2 pi. So they're not asking us to find all the maximum and minimum values on this function. They're just asking us to find them in one revolution. So same thing, I'm going to find f prime of x. Okay, I'm going to find f prime of x. I'm going to completely simplify. And then I'm going to solve for when f prime of c is equal to 0. I'm going to find my critical numbers. And then I'm going to do that sign test. And that sign test is pretty big, huh? Remember, you can plug it into all the factors, or you can just show yourself plugging it into f prime. I'm okay with either. But you got to have the table. All right, so let's take the first derivative. Okay, so the derivative of cosine squared of x, I'm going to take the 2, I'm going to bring it down. And this is going to be 2. I leave the cosine of x alone, and then I'm going to multiply by the derivative of the cosine, which is the negative sine of x. Next, I'm going to take the derivative of 2 sine of x, and it's just going to be the minus sign goes along the right, negative 2 cosine of x. So I am going to simplify. I'm going to factor a 2 cosine of x out. of each one. I'm actually going to factor a -2 cosine of x out because I can do that. And I'm going to end up with sine of x plus 1 on the inside. Okay. All right, so done. Completely simplified. And again, remember, I know that it's simplified because I've written it as factor times another factor, right? Times another factor. It's all split up. So now I'm going to solve it for when it's equal to 0. I'm going to take each factor and set it equal to 0. So I've got -2 cosine of x equals 0. And we know that cosine of x equals 0 when x is pi over 2 and 3 pi over 2. And for the other one, I'm going to take sine of x plus 1 and set it equal to 0. I'm going to subtract 1 from both sides. And I'm going to solve for when sine of x is equal to -1. And sine of x is equal to -1 when x is equal to 3 pi over 2. So neat. Notice I have some overlap here. Here I've got a critical number of pi over 2. And I've got a second critical number of 3 pi over 2. All right, so let's do a sign test. So I've got my endpoints here. I've got my endpoints at x equals 0. Give myself lots of room. And then I've got my next critical number at x equals pi over 2. Give myself some room. My next critical number at x equals 3 pi over 2. And then my final value of x equals 2 pi. And then I'm looking here at my functions, right? So I've got my factors of my -2 cosine of x. You can write those separately. It's up to you. And then sine of x plus 1. And I'm going to plug those in and look at the cumulative effect. Or again, you can just plug it into f prime of x. So remember, you're plugging it into f prime of x. This is the one you're plugging it into right here, not your original function. So if I pick a number between 0 and pi over 2, let's just say pi over 4. Okay, so I'm going to pick a number between that, which is pi over 4. So for between pi over 2 and 3 pi over 2, I'm going to pick pi. And then for 3 pi over 2 to 2 pi, I'm going to pick 5 pi over 4, I think is over there. Yeah. So if I plug pi over 4 into cosine of x and then multiply it by -2, I'm going to get a negative number. If I plug pi over 4 into sine of x and then add 1 to it, I'm going to get a positive number. And then a negative times a positive is going to give me negative. That's going to be that cumulative effect there. So this is that total. But also we can just plug pi over 4 into f prime of x and we'll see that it's going to be negative. So that means that it's going down here. I don't really have room at the top to write it. So next I've got a critical number at x equals pi over 2. So I'm going to plug in pi. So plug pi into cosine of x and multiply it by -2. I'm actually going to end up with a positive, right? End up with a negative times a negative is positive. Plug pi into sine of x plus 1, and I'm going to get a positive number. And then I'm going to look at the cumulative effect. Positive times positive gives me positive. I also can just take pi and plug it into my derivative and see that it's going to give me positive. So this is going to be increasing. All right, so I can see right here at x equals pi over 2, I've got a sign change, and this is going to be a minimum. So now I'm looking at my next interval of values from 3 pi over 2 to 2 pi. I've picked an in-between value of 5 pi over 4. Did I even write 1 pi over 4, 2 pi over 4, 3 pi over 4, 5 pi over 4? Nope, I need to do 7 pi over 4. Sorry. It's a bad choice. You probably knew that already. Anyways, so 7 pi over 4, I'm going to plug that in. I'm going to plug that into cosine of x, which gives me a positive. Then I'm going to multiply it by that pesky little -2. Don't forget that. That'll change your sign. And that's going to give me a negative. So positive times negative gives me negative. If I plug 7 pi over 4 into sine, and then I add 1 to it, I'm going to get a positive number. And then the cumulative effect of positive times negative is going to give me negative. But I can also just take 7 pi over 4 and plug it into my first derivative, the whole thing together. I can see that that's going to give me negative. If that's negative, that means that the derivative is decreasing. And so over here at x equals 3 pi over 2, I'm going from increasing to decreasing. So that means that this is a maximum. So now let's go ahead and write up our conclusions. So I've got a minimum point at x is equal to pi over 2. That's my critical number here. And if I take pi over 2 and I plug it into the original function, I'm going to get -2. And I can either write the ordered pair or the x-coordinate, depending on what they're looking for when they ask you the question. And next, we did find a maximum. So we've got a maximum at 3 pi over 2. So we're going to plug that into our original function. And that's going to give us 2. Again, it just depends on what they're asking for. If they're asking for the x-coordinates or the maximum and minimum values. Well, these are your final answers.